Okay, hey guys, we're going to do energy part 2 today. It's just mostly a bunch of practice problems I'm going to go through with you, um, kind of based on the information that we learned on page 38. So first practice problem says you mix sodium hydroxide with hydrochloric acid in a beaker to produce sodium chloride and water. Okay, the thermometer inside the beaker indicates the temperature is increased from 19 to 48 degrees Celsius. And here's the reaction. Okay, so how will the beaker feel when you touch it? Okay, well, if the temperature increased on the thermometer, the beaker's going to feel warm or hot or whatever. Okay, so let's think about what is the system and what are the surroundings. So the system is this right here. It's basically these chemicals right here. This is our system. So everything outside of that is going to be the surroundings. So that includes the thermometer. The thermometer is part of the surroundings. So the temperature increased there. When I put my hand on it, my hand is part of the surroundings. So if I'm feeling it with my hand, it's going to be warm. Therefore, the energy is flowing from the system, from here, out to the surroundings because it's feeling warm to me and I'm part of the surroundings. So that's an exothermic reaction. Okay, and that's because heat is being released, it's going from the system to the surroundings. So it says draw an energy diagram showing the change in energy before and after the reaction. Okay, so what's an energy diagram? Remember, an energy diagram is what we were looking at here on our notes from the other day, these little guys. Okay, since we know it's exothermic, we know it's going to start high, have a little hump, and it's going to end low. Okay, so we're going to draw one of these, and I just need energy over here, so I'm just going to label this one energy because it's an energy diagram. And then this one, sometimes they'll label it time or reaction pathway. So let's do reaction pathway. Now, RXN, that's just an abbreviation for reaction. So if you see that, that's what that means. So again, this is exothermic. So if it's exothermic, it means it released energy. So it started at a higher energy. You always have to have a little hump of activation energy, and then it's going to end lower. Okay, something like that. So if I ever say, hey, draw an energy diagram for an exothermic reaction, you know it should look something like that, where you start high, you end low. Okay, that's it. Let's look at number 2. It says you mix sodium carbonate and ethanoic acid in a beaker. The reaction is shown here. A small pool of water in contact with the outside of the beaker freezes. Okay, so here's our reaction. You don't really need it, it's just there. But let's think about what's our system, what's our surroundings. So again, let's define the system as this reaction itself, these chemicals being mixed together. So it says there's a small pool of water in contact with the outside of the beaker. So there's a beaker here and there's like a pool of water over here. That's going to be part of the surroundings, okay? And it freezes, meaning it definitely got colder, right? That means that the heat was taken from it. So if your reaction here, these chemicals are absorbing the heat surrounding it, that that would feel cold, right? Because it's freezing the water around it. So that would be an endothermic reaction because it's absorbing the heat from that pool of water, making it freeze. Okay, it's taking the heat away. It's taking the heat in. So it's endothermic. Okay. Okay, draw an energy diagram showing the change in energy before and after the reaction. Okay, so again, this is endothermic. So if you remember from our notes yesterday, endothermic reactions are going to start lower. They're going to absorb energy, so they're going to end higher. Okay, so it's going to be like an uphill. So let's draw this again. So again, this is energy, and then we'll call this our reaction pathway. Okay, so remember it's endothermic. So we're going to start here. We're going to go up a big hill and then kind of level off like that. Not perfect, but it's fine. So that should be the general shape, of any endothermic reaction you have, okay? All right, let's take a little sidestep here. This is kind of related, kind of unrelated, about collision theory, if you've ever heard of collision theory. So what's collision theory? So basically, it's saying it's theorizing basically what does it take for a reaction to happen? Because reactions don't always happen. So what does it take for a reaction to happen? So collision theory says in order to react, molecules must collide correctly. So the molecules have to actually come in contact with each other, and when they do, they have to collide correctly. What does that mean? They have to collide with the correct orientation. So here you have a little picture. It's kind of tough to see, but it's basically saying A is going to collide with with BX to make B and AX. Well, if they don't collide, if A doesn't collide with the right side of the molecule, like the X, then the reaction is not going to be effective. It's an ineffective collision. It's not going to happen. So the particles need to collide in the correct orientation, okay? And they also need to collide with the correct amount of energy. All right, if they don't collide with enough energy, then the reaction's not going to happen either. So there are certain things we can do. Oh, this is really hard to read. You might be able to see it on yours. It says more collisions is more proper probability of correct collisions. Therefore, you're going to have higher reaction rates. So there are things we can do to try to get a reaction to occur or to occur more quickly. So what are some ways we can do this? First is by using a catalyst. And we talked about this briefly on our notes yesterday. And a catalyst is something that is not consumed in a reaction. So it's something, maybe I'll just put that in parentheses, not consumed. So it's not really part of the reaction, but a catalyst can do a couple different things, but it basically can help sometimes, and you talk about catalysts a lot in biology, like enzymes are catalysts. They can basically kind of help put the molecule in the correct orientation so that when the collision does occur, it's more likely to be an effective collision. Okay, and that happens a lot in our bodies with our biological systems, is those catalysts can orient those molecules in the correct orientation so that when collisions occur, that reaction is more likely to happen. So that's kind of a catalyst. And what it does is it lowers the activation energy. So lowers the activation energy. And if you, activation energy really should be like that. Energy of activation. That's activation energy, if you ever see that. Activation energy is the top of the hump right here. The top of the hump is the activation energy. So if I was to use a catalyst, instead of my hump being up here, my hump might be like down here. So it's still going to have a hump, but it's not going to be quite as tall if you use a catalyst, okay? So that's one way we can speed up a reaction. Another way we can speed up a reaction is by increasing the concentration. Increasing the concentration. Increasing the concentration of your reactants. Because then there's going to, if it's more concentrated, there are more particles there. When there are more particles there, they're more likely to collide. So you're going to, have a faster rate of reaction. Another thing you can do is increase the surface area. Increase the surface area. Surface area. Increase the surface area. What do I mean by that? So like if you have a big chunk of crystal and you want it to react, and how can you increase the surface area? You can crush it up into like a powder and then maybe try to dissolve it in your other reactant or whatever it is you're trying to react it with. And that's going to make it react a lot faster. Okay, so instead of having things in like a big chunk, if you break it up into like a larger surface area, meaning spread it out into a powder, it's there's basically more room for those particles to interact with it rather than if it's in one big crystal. Okay. Okay, next thing is increase the temperature. Increase the temperature. And you guys know that when you increase the temperature, particles move faster. And when they move faster, they're going to collide more. When they collide more, then your reaction is going to happen faster. That's what it says here. Higher reaction rate. Okay. And the last one is we could increase the pressure, and that's for gases. Increase the pressure. And then in parentheses, that's an R. In parentheses, we'll put for gases. Okay, so if you increase the pressure of a gas, whether by decreasing its volume or what have you, you guys know that pressure is basically synonymous with collisions. So if you're increasing the pressure, you're increasing the collisions. And when you do that, they're going to collide more, and their reaction rate is going to increase, okay? So those are ways you can speed up reactions. Okay, let's flip over here. We're going to kind of go back now to our energy diagrams here, and we're going to do some practice problems with these. All right, so the first one says, reaction 1. So it gives us a few numbers, and it wants us to basically plot the the energy diagram. These are sometimes called potential energy diagrams. So the potential energy of your reactants is 250 kilojoules. So that would be right here. So I know it's kind of off a little bit. These numbers go with these thicker lines. Okay, so 250 would be between the 200, the dotted line between the 200 and the 300. So those are that's the energy of my reactants. It says potential energy of activated complex, So I'm going to underline that and put an arrow, and you should too. And this is also sometimes called the transition state. And then let's put in parentheses top of hill. The top of the hill. It's sometimes called, like in your notes here from yesterday, they call it the transition state. Sometimes they'll call it the activated complex. So that basically means the top of the hump or the top of the hill is going to be 350. So that's going to be this next dotted line between 300 and 400. And then it says the potential energy of the products is 300 kilojoules. So 300 kilojoules is right here. Okay, and so now that we have all three of these things, we can draw our diagram. So it's going to go up here, there's going to be a hump, and then it's going to come down here and level off right there. Okay, so it says, is this reaction exothermic or endothermic? Okay, so this reaction is going to be endothermic. Why? Because you're starting low, you're absorbing energy, and you're ending higher. Okay, it's uphill, so that's going to be endothermic. What's the value of delta H? Okay, so delta H is your difference between your reactants and products. So it's the difference between the bottom, where you started, and where you ended, basically. So this right here is delta H. So if I started at 250, I ended at 300, that is 50 kilojoules. Now for delta H, you want to keep in mind, okay, is this negative or positive? If it's endothermic, it's positive, okay, because we gained 50 overall, so that's a positive 50 kilojoules, okay? What is the activation energy for this reaction? Activation energy is the difference from where you started to the top of the hump. It's the energy you required to get it going, okay? So this is the activation energy. So I started at 250. The top of the hill was 350, so that's a difference of 100. So I went up 100, so 100 kilojoules. That's my activation energy for this reaction, okay? Okay, let's do another one. These are types of questions you'll see on your test, okay? Reaction 2. So it tells me my potential energy of my reactants is 350. So let's mark that. 350 is going to be right here in between 300 and the 400. And then it says the activation energy. So keep in mind, it's not telling me the potential energy of the activated complex like it did here. Instead, it's telling me the activation energy. And what is activation energy? Activation energy is basically the energy it takes to get to the top of the hump. So if the activation energy is 100, that means I'm going to go up 100 from here. I know the top of my hump is going to be 100 higher. So if I'm starting at 350, I know I'm going to go all the way up to 450 to get to the top of my hump. And then it says the potential energy of the products is 250. So that's down here. It's going to look like that. Okay. Is this reaction exothermic or endothermic? Okay, well this one, you always have to start with some kind of uphill, but look at where you start and where you end. This one, you started low, you ended high. This one, you start high, you end low. So overall, that's a downhill, so that's exothermic. Okay, and you can tell because it starts with more energy than it ends with. Okay, so starts with more energy. Starts with more energy. What is the value of delta H for this reaction? So delta H, remember, is the difference between where you start and where you end. So I started at 350, I ended at 250, right? So that I went down 100 kilojoules, but it's negative. Why is it negative? Because I basically lost 100 kilojoules. Okay, so when it's exothermic, your delta H is always negative. Okay, what is the energy of the activated complex? So what's the energy of this guy up here? That's basically saying what's the energy of the transition state, the tippy top of the hump. That would be 450 kilojoules, right? Because that's this very tippy top. Okay, all these sorts of questions are sorts of questions I could give you on a test. Okay, last one. It says, okay, potential energy of the reactants is 200. Potential energy of the activated complex, so that's the top of the hump, is 400. Okay, so it's going to go up there. And then it tells me the delta H. So remember, delta H is the difference between where you start and where you end. So I know where I'm starting. It's positive. So if it's positive, that means I'm going to end higher because I'm gaining overall. So I need to go up 150 from where I started here. So I'm going to go up 150 from where I started there. So I'm going to end, I started at 200, that means I'm going to end at 350. So it's going to be like that. Okay. Okay, so is this exothermic or endothermic? Well, because we went uphill and this is positive, we know it's endothermic. If your delta H is positive, it's endothermic. What is the energy of the products for this reaction? Well, we just said the products are going to be at 350, right? What is the activation energy for this reaction? So activation energy is remember, it's the energy it takes to get it going. So this is the activation energy, EA, that's activation energy. So I went from 200 to 400. So that would be a 200 kilojoule activation energy. Okay? All right, and that is all.